Good afternoon, this is Schweitzer. We're going to run a little video here on ionic properties, and the property we're specializing here is solubility. Alright, so why do things dissolve? How do we model solubility? That's really what we're looking at here. So a couple things we might mention here is, okay, well, first things first, why do things dissolve? Well, in this sense, we're looking at there has to be some sort of an attraction. If I have, let's say, a liquid here, this is what we typically call the solvent. And for stuff to dissolve in here, if I just drop a rock in here, big or small, it's just going to fall to the bottom. Gravity grabs a hold of it. But if something dissolves, that must mean there's some sort of attraction between what we call the solvent, and this little guy here is called the solute. There has to be some sort of attraction between the solvent and the solute to allow it to stay in there. So keep that in mind. These particular attractions are common in chemistry, and we will talk about them more as we move along. But next up here, how do I model this particular idea? Well, it turns out that when ionic compounds dissolve in water, they break apart. This is actually a molecule, and you could make a model of this molecule using what's called a Lewis dot structure that's coming. But just so you know, that's a uniquely held together molecule. It breaks at the ionic bond right here. I have my cation and my anion. Aqueous means dissolved in water. Keep the charges on here because that's the reason why it's soluble. We'll show a couple different other ways of doing this, but essentially this dissociation is extremely common for ionic compounds, not for molecular or covalent compounds. We'll be trying some examples of these. Alright, so how do I go about modeling this? There are a few different types of problems and ways we can do this. First one, solubility for aluminum chloride. Let's just do that first. Let's write the formula for this. So aluminum chloride will break apart into its cations and anions, which is 1 aluminum and 3 chlorides. Alright, and the way I would show this is two different ways. One is I could show, okay, in a solution what to look like. I have this just breaking apart. I have aluminums and I have chlorides. Now the chloride, you will notice, this guy has 3 energy levels. This guy only has 2 energy levels. It's isoelectric with neon. So I might draw one smaller one and 3 bigger ones. And I would want to draw them separated. And if I didn't put the name inside, I'd want to make a legend that this is the chloride ion and this is the aluminum plus 3. To indicate your charges. That's one way of doing it. This is one model, this is another model. Another way of showing this would be really to show how it attracts the water molecules. So I want to add some water molecules. Well, the water molecule looks like this. This is the oxygen, and these are hydrogens. The oxygen has a partial negative charge. We draw that thing like this. Okay, partial negative, and this side is partial positive. Partial positive. Small positive on this end, small negative here, which is what the attraction is. So I wouldn't necessarily show that. I would just kind of show it like this, that my positive end is attracted to the negative end. I would not want to turn it around and put two positives together. This is again another example of Coulombic attraction. If I had a chloride ion here, I'd want to put the positive ends around that guy. Another name for solubility is salvation, and you can see that this thing is sort of clustering around these ions. Two different ways in which problems can sometimes be added. Alright, so go ahead, let's write out the dissolving equations for each of these and let's just draw them out. Go ahead, give them a try. So this is calcium oxide goes to calcium plus 2 plus O negative 2. And size-wise, calcium and oxygen is going to be the small one. and the calcium 2 plus might be a little bigger. You could draw more of them, but in this case, just one, some multiple of this. Alright, copper 2 chloride goes to Cu plus 2 Cl negatives. Chlorine will be, the copper will be having 4 energy levels, the chlorine is 1, so I might draw a bigger copper and 2 smaller chlorines relatively. Ammonium sulfate, okay, this is going to be an ion here, so it's going to be 2 ions, so NH4 parentheses 2 SO4 goes to NH4 plus SO4 minus 2. Size is going to be a little bit more difficult to do here, but the ratios should be kept up. So this is going to equal NH4 plus, and this is going to equal the SO4 minus, and I'll have 2 positives and 1 negative. This is a negative 2, so the charges always balance in these solutions. Charges will balance. Let's say, well, I got 2 positives and negatives, right? So how's that balancing? Well, this is a minus 2 and a positive 1, so they will balance. Another property of dissolved solutions is called an electrolyte. This is a aqueous solution that will conduct electricity. Why is it conducting? Because it has free-flowing ions inside. Free-moving ions. Non-electrolyte, okay, does not conduct, not a conductor. Some people might think that plain water is a conductor of electricity, and it just simply is not. The ions inside it will. So here we have lots of ions present here. So we call this a strong electrolyte. This is only got a couple of ions here. We call it a weak electrolyte.